You know, I wish I could tell you, but I don't think it's a good idea to tell you lies, because you'll find out I'm lying pretty quickly. I wish I could tell you that, oh, we're going to start a nice, easy section after all that hard work of doing the midterm. The truth is, we're going to start a ridiculously ugly, difficult section. And it is. And it's a very niche market. We are going to find out how to integrate fractions that have ugly square roots in them. And we're going to do it by a technique that they're calling trig substitution. I prefer my own name for this, and this is the name I tend to use. I tend to call them X subs. You know how we do normal substitution? It's U subs. I use that term a lot. Well, these are substitutions as well, but these are called X subs. And they basically follow the same pattern that U subs do. What makes them ridiculously ugly? Number one, they are extremely long. It takes forever and a day to do one. So you might look at the homework and say, oh, 7 questions, no big deal. These 7 questions will take you as long as 21 normal questions would take. So it's actually a big chunk of homework. So number one is just the length. Number 2 is complexity. These are not simple processes. These are quite complicated, quite complex. And so you will have some issues with that. And thirdly, they involve trig. And I think most people, the minute you involve trig, you just up the level a little bit. So suppose you're trying to integrate. Ah, there's one of the 2 people that's still to come. Suppose you're trying to integrate this, right? Who cares what's in top? This is the important bit. There's a square root of x squared plus 9, x squared plus 29, you know, x squared plus 1,000,000, whatever it might be. When you see that, you're going to use the substitution x equals a tan theta. When the square root has x squared, take away a squared, you know, like x squared minus 9, you're going to use the substitution x equals a secant theta. And lastly, when it's a squared minus x squared, basically switch these 2 around, you're going to use x equals a, oops, I forgot my a sine theta. What I've got down here are some trig identities and some trig integrations, and I'm sure I've got more, and when I end up using them, I'll stick them here. So let's go right in and show you an example. Suppose I wanted to integrate, right, let me find a question that's like this one so we can use it as a template. Put solution here. Give it a second to kick in. All right. And okay, here we go. X squared over the square root of 1. Oh, we'll make it 9. Yeah, that's nicer. 9 take away x squared dx. Right. Hold on a second. I'll just mute everybody. We're getting some background sound. My problem is, where is the mute? It's different. It's not where it should be. Okay, where are you hiding? I don't know. I don't know where it's put the mute button. Rena, you're making a lot of noise. Stop doing it. I'm looking for the mute button right now. Where the heck are you hiding? Right, let's close. No, that's not good. Okay, Rena, can you hear me?
Oh.
Hi, Rena, I'm trying to find the mute button because you're making a lot of noise and I can't find the mute button. So you're going to have to stop me. You're going to have to be, this is annoying. Right, yeah. I don't know where the mute button is, guys. I should never have updated Zoom until the class was finished and then I could play about with it. So I don't know what I'm doing now. I'm lost. I know what I'm doing. We are looking at how to integrate this. So I'm just going to continue from where I left off and hopefully that mute button will appear somewhere. It's probably in a sub menu somewhere that I can't see. Right. It looks like, I don't know, I'm going to call them some. This is 1, this is 2, this is 3. Right. This guy looks like number 3. That means you make this substitution. X equals a sine theta. If you want to think of this as being a squared, that means this fella. Okay, so the first thing you're going to do is you're going to figure out which one of the 3 to choose. So step 1 is basically choosing that guy. Now, once you've chosen this guy, you do your differentiation. Only it's now going to be dx by d theta, which is 3 cosine thetas. And then it's going to be dx is equal to 3 cosine thetas d theta. Have you noticed that it's not the normal way a substitution works? Wouldn't a substitution be u equals 3 sine x or theta equals 3 sine x? Have you noticed that this is x in terms of theta rather than theta in terms of x? And that makes that a little bit different. One of the differences is, do you notice that you only need 3 lines to isolate the dx? Not a biggie, but that's what happens. Now, just like normal substitution, you go over here, and every x gets replaced by 3 sine theta. That's good. Times dx, which gets replaced by 3 cosine theta d theta. And we'll call this bit step 2. So step 1 is find the correct x sub to use, do your differentiation and isolate the dx. Step 2 is to take all of the pieces and replace the x's with 3 sine thetas and to replace the dx by whatever this is. What do you think I'm now going to do? Any suggestions for what I should do now with all this stuff?
Identities or?
Well, eventually, yes. Probably a good idea to multiply things out and collect terms and then start looking for identities, yes. So 3 sine theta times itself is 9 sine square theta times 3 cosine theta d theta. And on the bottom, we've got the square root of 9 take away 9 sine squared theta. And I've just thought of some guys to put in here. It's the same kind of trig identities that we used in the previous section. So, see this square root guy? He is always going to disappear. Right? He's going to become something much nicer and not be a square root anymore. So on the top, the 9 and the 3 is going to get me 27. I've got a sine squared theta. I have a cosine theta. I have a d theta. Has anybody got any inkling about how I'm going to make this nicer so that the square root goes away? Take it small steps. Do you notice that there's a common factor of 9? So I'll pull that out. If you look at my little list over here, isn't 1 minus sine squared cos squared? So 1 minus sine squared is cos squared. Isn't the square root of 9 3? And the square root of cos squared cosine theta? Do you see how the square root has disappeared? So this is 3 cosine thetas. What do you think I can do with this fraction that might make it prettier?
Simplify to 9 sine squared theta.
Okay, let's see how we did that. Cancel the cosines, right? 3 goes into this, just like you said, 9. And it has got nicer. So far, so good. Now, when you get to about here, so step 3 would be essentially simplify as much as you can. Your question now takes a new direction. We're now going to have to figure out how to integrate a trig function. Now, in this particular case, it ended up being 9 sine squared. Can you imagine the next time it might be 9 sine squared theta cos cube theta? Or it might be 9 tan cube theta secant squared theta, right? All the kind of combinations that you got from previous situation. This guy needs to be integrated. Can you remember what we did with a sine squared on its own? And I'll start it off. Wasn't there a half involved? So what does sine squared theta look like? Sine squared theta? Nothing yet?
1
That's
minus, is it
Yep.
cosine 2 theta? I don't remember.
You nailed it. Yeah. So sine squared becomes 1/2 1 minus the cosine of 2 theta. So when you want to integrate a sine squared, or for that matter, a cos squared on its own, if it's just a sine squared on its own, or just a cos squared on its own, you use this identity here, right? Now, all I'm doing here is distributing the 9/2. Now, I should be able to integrate this. 9/2 becomes 9/2 theta. Okay, a little bit trickier here. Forget about this negative 9/2 right now. If you integrate a cosine of 2 theta, don't you get a positive sine of 2 theta? Remember the linear shortcut method. Times what fraction? If you integrate
1/2.
1/2. 1/2 joined with the 9/2 is where that 9/4 comes from. The negative's still there. Yay! We have integrated our guy. So step 4 will be to integrate our trig function, our trig expression. Now that's, I know I've been doing a lot of talking, that's taken us over 10 minutes. And you might think, well, that was kind of long, but it's not finished. We're only about 2/3 of the way through. We still have 1/3 of the way to go. And the reason we're not finished is that this answer is in terms of theta. But the original question had x's. So we are expected to convert this fella, all these thetas, into x's. And that's the last phase of the puzzle. How do you convert this thing into x's when really the only thing you've got to work with that has an x in it is that? So this is the process. This final part is pretty much the same each time. Isolate, in this case, the sine theta. And then we're going to use a guy called SOHCAHTOA. Who do you know in SOHCAHTOA for sine? What's the ratio for sine?
Do you mean like opposite over hypotenuse?
That's exactly what I mean. Yes. So if the sine of theta is x over 3 and the sine of theta is opposite over hypotenuse, does it not make x over 3 the same thing as opposite over hypotenuse? And what that allows us to do is to build a right angled triangle. And this is all leading up to turning these things here eventually into x's. So if I call this angle here theta, then this side here will be the opposite, this side here will be the adjacent, and this side up here will be the hypotenuse. So the opposite is x, the hypotenuse is 3. How am I going to find the third missing side? How will I be able to find out what adjacent is in terms of x?
Tan?
Not without using SOHCAHTOA,
Oh,
a different thing. Can you remember Greek guy? Right angle triangles?
Pythagorean's theorem.
That's the guy. So if you want to get the third side, isn't it the square root of this guy, which is 9, take away this guy, which is x squared? The third missing side has got an ugly square root in it. If that's the same ugly square root that the original question had, that's really good news. It means you've been doing it right. So now I have got this triangle. I should be able to convert anything that this is. We just happened in this question to get 9 2/2 and the sine of 2 theta, but you know, it doesn't really matter what you get. You can use this triangle to come up with the answer. So let's show you how it's going to work. I want to find out what that is equal to. Right. Well, I know that the sine of theta is x over 3. So won't theta be the inverse sine of x over 3? So 9/2 theta is 9/2 the inverse sine of x over 3. Okay, I want to know what the other piece is. -9/4 the sine of 2 theta. Well, if I'm going to use this triangle, it's really only built for sines and cosines and tangents. It's not directly built for sine of 2 theta. So I guess I'm going to put it in here. The sine of 2 theta is 2 sine theta cosine theta. Do you remember that one? The sine of 2 theta is 2 sine theta cosine theta, which means this fella is -9/4 times 2 sine theta cosine theta. Well, -9 to m cancel, you get -9/2. Sine theta, opposite over hypotenuse. Opposite over hypotenuse. Cosine theta, adjacent over hypotenuse. Three cancels with the 9. You are left with that guy. So your final answer, this fella here, is 9/2 the inverse sine of x over 3 minus 1/2 x, this square root, plus c. That just took over 20 minutes. One question, 20 minutes. And we've 2 more to go. So this guy is going to be the guy that you use when the substitution is an x equals, where we go, 3 sine theta, 2 sine theta. So if you ever use a sine theta, it's going to look like this guy here. I think I was being fair when I said this is a really ugly question. No argument about that. The only saving grace is that once you've done one, the rest of them pretty much follow the same theme, right? So there is a process. That's about the only saving grace. So I'm putting that one in the bank. Let's go for our next guy. I wonder if it's here. No, I do not know. It's distracting me where the mute button went. Hope I haven't scared poor Rena out the road. Rena, are you okay? We can
Yes.
talk. All good. I hope I wasn't rude. If I was, I apologize. I'm not good with multitasking, and you just happened to be here, and I couldn't find my general mute button.
Sorry.
So you okay?
Mhm.
So I'm apologizing because I may have came across as a bit, I don't know, a bit cruel. I don't need to be. Right. Okay, we have done, I better put a little check mark on it. We've done an A sine theta kind of situation. I'm now going to find another guy to do. Who shall we do? Let's do this fella. This is similar to question 5. It's going to be the integral of the square root of x squared take with 25 over x cubed dx. Okay, now, oh, we're still on white screen. Okay. X squared minus 25 is the key here. Can you see x squared minus a squared? That makes it number 2. And that means that we're going to do the substitution x equals a secant theta. So we're going to do x equals 5 secant theta. Are you happy about how I decided it was that one rather than any of the other 2?
Just to make sure, the denominator is x cubed.
Yes.
Okay, thank you.
Okay. So if you differentiate x with respect to theta, what is the derivative of the 5 secant theta? Oh, that's an interesting pause. What's the derivative of 5 secant theta? Or just secant theta will do.
5 over the cosine of theta.
Five secant tan. Okay? 5 secant tan. What's the derivative of tan theta? Because that's going to be the next one after this. What do you get if you differentiate a tan? We need to brush up on our trig, guys. You can't have,
Secant squared.
that's the guy, right? You can't have these guys floating out where you have to go rummaging every time. These questions are difficult enough without you breaking up your thought process for hunting for, I wonder what this is, and how do you turn that into something? And I don't know what that is, and I don't know how to fix it. And that will not be a pleasant day for you. You need to try and get the basics, right? Derivatives, integrals, and some of these trig guys in your brain just so that they're there when you need them. So when you do the crossover, you get 5 secant tan d theta. Have you noticed again that you only need 3 lines to get the isolated dx? Now I've got a square root. X squared take away 25 turns into 5 secant theta squared take away 25. The x cubed becomes 5 secant theta all cubed, and the dx becomes a 5 a secant tan d theta. Now, just like the last time, aren't we going to work on this to make it as pretty as possible? So let's see what we get. To save a line, won't that be 25 secant squared take away 25? So I'm going to pull out 25 as a common factor. So instead of 25 secant squared take away 25, I'm writing it like that. I'll just leave this guy untouched. And on the bottom, I get 5 cubed, which is 125 secant cubed. So far, so good. Okay, can you see any cancelling? And anything that can be changed into something else? Well, let's look for cancelling. Can you see any cancelling?
You can cancel 1 secant off the bottom.
Okay, so that's going to leave me with a secant squared. Can you cancel a 5 and a 125 while we're at it? It's not much, but it's better than nothing. Agreed? And that leaves you with 25. Doing this guy here over at the side. Every time you do these questions, the ugly square root is going to disappear. It's guaranteed, or else the question's just not going to work. So I'm putting you on the spot again. What is secant squared theta minus 1 the same thing as?
Tan squared.
Yeah, we're on a roll. That makes this fella turn into 5 tan theta. So on my next line, I'm going to have 5 tan theta, gone and gone, another tan theta. And on the bottom, I'm going to have 25 secant squared theta d theta. So far, so good. Okay, where are we off to next? Anything else I can do? Even if it's only minor, let's do it.
You can cancel the 5 and 25.
Yeah. And can't I join these two tans together and give myself a tan squared over a secant squared? And what have I got? 5, I guess, in the bottom, right? And now you're at this point here where we have to figure out what on earth we are going to do. And what you get is very variable. There's no rhyme or reason to it. You just get what you get. This guy has got tans in it. Yep, this guy has got secants in it, but they're not next to each other. So that doesn't, and that isn't going to involve the techniques that we used from the previous section. I mean, if this had been tan squared, secant squared, I guess I could have done that, but no. Sometimes you just have to figure out a one-off way to fix it. Oh, do you see this 5 in the bottom? Can I just kick it outside and call it a 5th? Numbers just get in the way sometimes. That's not much of a fix. I think I'll do it over here. I don't think you've seen this combination, so you're just going to brainstorm, which means whatever comes into your head, you'll tell me and I'll say, nope, that doesn't work, but that's fine. You might come up with a strategy that does work. Eventually you will.
Can we
But
put them in terms of sine and cosine?
God, you nailed it in one go. I was expecting to get 2 or 3. Yeah, that wouldn't work, but it was a good idea. But the first idea I heard worked straight away. Why did you pick that? It was interesting you did it so quick.
That's just what I always do if I'm stuck.
That's a good strategy. If I can't think of anything else to do, just turn them into sines and cosines. That's a good strategy because aren't you comfortable with sines and cosines much more than tans and secants, right? I think most people are. Let's see what this turns into. Sine squared theta over cos squared theta. That's what tan squared is. Over a 1 over cos squared theta. Now, superficially, you might think, oh, God, that's impossible. But don't talk yourself out of a good idea. If you've got a fraction on the top and a fraction on the bottom, can't we think of that as being the top guy being divided by the bottom guy? And isn't one fraction divided by the other the same as one fraction multiplied by the reciprocal of the other? And guess what happened? Bingo. That guy, actually there's a 5th floating about, right? Is 1/5 the integral of sine squared theta. That is so cool. That is not the only way to tackle that question, but I like that one, so I'm keeping it. It is possible with trig that there are other ways in which to do that. Just on the off chance, has anybody got any other ideas of how you might tackle this? And it involves an identity, as typically it does. Any other ideas about how you could tackle this fraction? Make it different, make it nicer.
Tan square theta could be secant squared theta minus 1.
Yes. And if you did that, you'd end up with some other bits, but in particular, you'd end up with 1 over secant squared. And you know 1 over secant squared is cos squared. So, well, let's show you, I've got room. Tan squared, what is it? Is secant squared minus 1. If you split this into 2 separate things, you get a secant squared over a secant squared. Take away a 1 over secant squared. But isn't a secant over itself just 1? And isn't 1 over a secant a cosine? So 1 over a secant squared is a cosine squared. And do you know what 1 minus cos squared is? Sine squared. You see, that was a totally different route to the same destination. Cool. Now, they're the only 2 that my brain's thinking of. Some of you might have thought of some other quite interesting technique, and that's fine. As long as it ends up being something you can integrate, it's allowed. Right, let's return back to this guy. What am I going to change sine squared into so that I can actually get the answer to the integral?
Half angle identity.
Yep. Which is basically, by sheer coincidence, no other reason, almost the same as what we did in the first example, isn't it? So if I bring out that half, you get a 10th. And that means I can just focus on this. So that's going to be 1/10 theta. A cosine gives you a positive sign with a half. So you get that. Now I'll distribute the 10th. And so the original integral, which is this guy, has now got this answer, but the answer is in theta. So we're about 2/3 of the way through again. Let's see how we finish it. You go back to your x sub. And you divide both sides by that. And then I'm going to do this. Because if I'm going to use SOHCAHTOA, don't I need a sine, a cosine, or a tan to do it with? If a secant is this fraction, and a secant is a reciprocal of the cosine, won't the cosine be this one? Basically turn it upside down. So I'll build my right angle triangle. I'll call this theta. We'll have an opposite. We'll have an adjacent. And we will have a hypotenuse. And a cosine is adjacent over the hypotenuse. That's what SOHCAHTOA tells us. And so the adjacent is going to be 5. The hypotenuse is going to be x. And Pythagoras tells us x squared take away 25. And we better have, and we do, the same guy. Now, I need to turn that guy into x's. I need to turn that guy into x's. Right, if cosine of theta is this, won't theta be the inverse cosine of that? So 1/10 of them gets you 1/10 this fella. What am I going to do about the sine of 2 theta? What am I going to change it into?
Would be the square root of x squared minus 25 over 5. Sorry, over x.
Oh, that may well be what it becomes. But all I was hoping for is that it's 2 sine theta cosine theta. And that will get us, well, that and that gets you a 10. So let's take care of that. Sine theta is this guy over x. And cosine theta is this guy over x. And the 10 and the 5 cancel down to give me a half. I'm going to have this ugly square root. And the 2x's get me x squared with a plus c. And that's what that piece is. So if you stick this guy at the front and then that guy after it, you've got the final answer. So it's 1/10 inverse cosine of 5 over x. That's what this piece is. Take away 1/2 that ugly fraction. And that took me 20 minutes. This is a lot of work. Right, I just get booted out of WebAssign, so I'm hoping to get back in. Okay, any questions about that fella? 1, 2, 3 pages. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 lines of working just to solve one question. That must be a world record for us. One question took 19 lines just to get the answer. So we have now done a secant version. So all I need to do is show you how to do a tan version, and you'll know how to do all 3 situations that you're going to come across. So let me go, oh, I don't need to go anywhere, it's in front of me. Question 1, that looks weird, never mind. X cubed over the square root of x squared plus 49. And this one has an x squared plus 49 look to it. So we're going to use an x sub of 7 tan theta. And so this little list here, you can just say, okay, it looks like that. This is what I use. Nope, it looks like this fella. Okay, that's what I use. Now you're going to cheer me up now. What is the derivative of tan theta?
Secant squared theta.
You got it. So the crossover is 7 secant squared thetas, d thetas. There's your dx on its own. Instead of x cubed, I'm going to have 7 tan theta cubed. The bottom's going to be square root of 7 tan theta squared plus 49. And the dx is going to be 7 secant squared theta d theta. Now, it's not uncommon for these questions for the number to become really, really big. So I'm going to show you a little trick you can use to try and make your life a little bit easier. This guy is just 7 cubed tan cubed theta. Now, I could go in my calculator and find out what horrendous number 7 cubed is, but I don't need to. I can leave it as 7 cubed for the time being. Times 7 secant square theta, d theta. And on the bottom, we have got 7 squared, which isn't that bad. So 49 tan squared plus 49. So I'm going to save a line of working by pulling out the 49 as a common factor and getting that. Now, just like in every other question, won't this ugly square root disappear and become something a little bit nicer? Tan squared plus 1 is over here somewhere. In fact, it's there. So tan squared plus 1 is going to get replaced by secant squared. That and that get me 7 to the power of 4. Tan cubed theta, secant squared theta, d theta, over the square root of 49 secant squared thetas. And the square root of 49 secant squareds gets you 7 secants. So the square root has gone. Is there any cancelling left? Can I do some cancelling?
You can cancel the 7s.
That's a good start. Go 7 cubed. Anything else?
A secant.
And when you cancel it here, you leave behind just a single secant. So we now have 7 cubed tan cubed theta, secant theta, d theta. And I'm going to pull out that 7 cubed because it's a number and numbers just get in the way of the thing. Now, I could leave it as 7 cubed until right at the end, like the last line, and then turn it into a number, or I could turn it into a number right now and just stick it outside the integral, whatever you prefer. But it's just a number, right? It's just 7 times 7 times 7. So now we have to focus on the integration part. This is kind of 1/3 done. This is the middle third. The other 2 questions ended up being things like sine squared and so on. This one is a U sub. So this one is from the previous section. And we have to decide what the U sub is going to be to make this one work. There are 2 possible U subs when you deal with secants and tan, isn't there? It can either be the U sub secant theta on its own, or tan theta on its own. That's the only 2 choices you got. Don't even think of others. What do you think it might be? Is there a 50-50 chance?
Secant.
Oh, you nailed it. Was that a gut feeling, or did you have a reason why you chose that?
The derivative of secant is secant tangent.
Which means I don't need to ask the next question. See how quick it is if you just know the answer. You don't need to pause and go look for it. So derivative is secant tangent. And secant tangent is good news because it uses up quite a few guys, and with a bit of luck, whatever's left over we can deal with. So it's going to be tan cubed theta, secant theta, followed by oh, I forgot something. It's a U sub. We still have to isolate, don't we? The d theta. I forgot about him. There we go. Now I've got you. So it's 1 over secant theta tan theta du. In other words, you use up some of them. In fact, you use up quite a lot. Don't you use up all the secants and one of the tans? So you are now looking at that guy. We have an orphan tan squared. We don't want tan squared. We want something with secant squareds in it. But I have a guy over here who's doing that exact job. Can you see that tan squared can be called secant squared minus 1? So this can be called secant squared theta minus 1, which means it can be called u squared minus 1, which is pretty much the question finished. Now, I've got a 7 cubed floating about here. Now that I've wrote that down, I'm thinking maybe I shouldn't have bothered. Could we just pretend it's not there and just remember to stick it at the end? That'll save us having to write it all over the place. So we have got to turn this guy back into secants. And that's 2/3 of the job done. So we are going to have to finish the question off now. We're going to do that by building the triangle. So we start with that fella. If you divide both sides, you get that fella. SOHCAHTOA tells me that a tangent is an opposite over an adjacent. This allows me to build my triangle. Here's my angle theta. Opposite, adjacent, hypotenuse. The opposite is x. The adjacent is 7. Pythagoras tells us that if you want the hypotenuse, it's these two guys squared and added inside a square root. And as a double, treble check, perfect match. You see it matching here. Now, the guys that we are trying to get the answers to, if I can find them, was 1/3 secant cubed and just a secant on its own with a minus, right? Secant theta is really the same as 1 over cosine theta. So I'm just going to find out what the cosine is and then turn it upside down. So if you want to do the cosine, it's adjacent over hypotenuse, 7 over this guy. So secant is, instead of 7 on the top and this on the bottom, you switch them round. And you cube them. And you stick a 1/3 on the front. And for secant on its own, you do a negative of just one of them. And so our answer was, here we go, 7 cubed, 1/3 secant cubed theta, take away secant theta. That became 1/3 this guy cubed over 7 cubed, take away just one of these guys over 7. Okay, I can actually kill that off and we're left with something that's actually a lot nicer than I thought it was going to be. This guy cubed. That doesn't quite cancel that, but it does cancel one of them, so I'm only 7 squared, which is 49. And that doesn't look too bad now. I'd say. Wow. That's an hour done. Are you still with me? You haven't went and run away screaming somewhere. That is a lot of algebra. It's a lot of trig, and it takes a lot of time. So you're all agreeing with what I just said. So that's true. Taylor, you've got a comment.
Can you share your screen real quick? I just need to write down the last bit. I missed it real quick.
Not a problem. Right. I'm going to give all our brains a few moments to just process all this information because there's an awful lot in it. And I'm going to see if I can remember a joke. Oh, has anybody got a joke for me? Any jokes?
Did hear one the other day.
Okay, go for it. What is it? What is the joke?
It's, why don't Germans have any fun?
Oh, we're going to insult Germans. Okay. I don't know. Why don't Germans have any fun?
Every time they do, somebody helps France. That was what I heard.
Oh, God. Right.
Not so good.
No, not so good. But I've told worse, so it's not your fault. I think I'd know how to insult the French, but I'm kind of wore out of French jokes. I don't know. No, I ain't got one. I think it's just my brain is fried because of all the heavy duty stuff that we've been doing. Oh, someone just did a joke in the chat, so let's see if we can do it. Why can't stairs be trusted? They're always up to something. There should be a drum thing, you know, dum 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 dum. No, I can't. I'm out of jokes. Jokes just come to me when they feel like it. I don't really plan jokes that much. Oh, I'll tell you a story. Oh, I started a band called Blanket. It's a cover band. True story about France and indirectly about Scotland. I've travelled a lot in Europe, but there was a time when I'd never been to Europe. And I do remember the first time I went to France. And what we did is we had our car and we drove down to Dover, and you get a ferry from Dover over to Calais, which is pretty typical. That was before they built the channel. And I remember when we were going across, I was thinking to myself, you know, you have stereotypes of what a Frenchman should look like, and real people don't follow stereotypes, right? Real Frenchmen won't be like that. So don't think that you're going to go over and you're going to see a guy with a little beret pedaling a bike and have a black and white striped top, you know, the kind of cartoon version of what a Frenchman should look like. You know? Like a German should be wearing lederhosen and have a funny little hat on with a feather, right? That kind of, with a jug of keg of, you know, lager in his hand, right? Whatever. And so we got to France, and when we got off the ferry, it was the days before terrorism and so on. It was a very smooth process. They just basically tell you to get off the ferry because they want to, you know, load it up with the people going the other way. So they weren't in any great interest to see who we were. And so we got off the ferry, and you just kind of follow policemen saying go left, go right, and then you hit the main street. And within 2 minutes of hitting the main street, because we arrived in like some ungodly hour, like 6 a.m. in the morning. And one of the first people I saw was a Frenchman on a bike with a loaf of bread under his arm. Okay, he didn't have the beret or the black and white stripe thing on, but he was darn close to being a stereotype. So go figure. So indirectly, why is that connected to Scotland? You might think that you're going to go to Scotland and people are going to be wearing kilts all over the place. Right? That's what Scotsmen do, right? We wear kilts and we talk funny. They don't typically do that. But when you arrive at the airport, you are going to see an awful lot of people wearing kilts. Mostly younger guys on holiday going somewhere. And wearing kilts, evidently, allows you, as they phrase it, to pull the birds. Evidently, if you're a guy and you're wearing a kilt, girls will come up to you and go, oh, you're wearing a kilt, where are you from? Blah, blah, blah. Right, you got your in. So you're alive at Glasgow Airport, and there's these 18 to 25-year-olds all wearing kilts. Well, not all of them, a lot of them wearing kilts. And so you'll arrive and you'll think, oh, it's just like I thought it would be. Scotland, everybody's wearing kilts. No, they don't. Very rarely do we wear kilts. I own a kilt, but you only really wear a kilt for very special occasions, right? Going to weddings, graduation ceremonies. I graduated, right, in a kilt, right? You would do things like that. But only special occasions. So if you see someone in the street and they are wearing a kilt, you can pretty much guesstimate that they're on their way to or coming back from some special occasion. For instance, I got married in my kilt. I own my own for obvious reasons. It's cheaper than rent. I'm not even sure you. You could probably rent a kilt in Scotland. A kilt in America, couldn't you? There's probably some place where they rent kilts. So anyway, when you go to Scotland, you will find out that the stereotype that we wear kilts is not true. We don't typically wear kilts at all. Which now I've got my brain, it's not a joke, but I even remember the word. Have you heard the term cultural appropriation? I dislike with a fervent vehemence people wearing what are called utility kilts. That kind of sort of offends me. If you're Scottish, you can wear a kilt, and if you want to wear a utility kilt, you know the ones that basically just grey or tan in colour, right? They're not real kilts. But they just annoy the heck out of me, and people wonder why it annoys the heck out of me. Can you imagine that you've got Mexican descent and somebody wears an exaggerated sombrero and they're not Mexican and they're walking about the street with it? Would that not offend the heck out of you? That's what utility kilts do to me. They just annoy the heck out of me. You know, why are you wearing that? You're not even Scottish, you know? Anyway, I got it out of my system. So any of you who've got a utility kilt, don't tell me, because I take 10% off your credit. Taylor, where are we? Have I meant to give you 10% or am I meant to take 10% off? I can't remember with you.
I haven't done it yet, but I talked to my parents about it last night, and it's definitely that I'm going to be doing it in the future. That's something I really want to figure out.
Okay. Taylor, the other Taylor, what are you going to say? Can't hear
I
you.
forgot there were two Taylors, so I got confused.
Yeah, so did I. My apologies, Taylor number 2. Do I owe you 10% or should I be taking 10% off your credit? I can't remember which.
I'd say probably giving 10%.
Yeah, that's probably the way you should go if I say I don't know what it is. Okay, let's get started. We're going to begin our next section today. We're looking at chapter 7.4. So let's make sure that I am on. There's some other jokes on chat if you want to have a quick look while I'm getting ready. Kind of take the strain off today. We're going to look at a technique called partial fractions. It's a kind of double whammy night tonight. I don't think they're anywhere as bad as trig substitution is. But they do involve quite a lot in the process. So let's give you a kind of intro to what is going on here. Can you imagine we have a fraction that looks like this? You can break a fraction into its constituent parts. So this fraction, you could break it into two different little fractions. These little fractions are called the partial fractions. That's where the name comes from. So in this section, we're essentially going to learn how to integrate fractions, but not nice fractions, ugly fractions, like this ugly fraction. Okay, so that's going to involve a lot of algebra. So we're going to do the skill building that you need to eventually get this done. So I'm not even going to, for a while, even look at integration. We're going to look at the algebra of how to break things apart and the way that they get broke apart, how you make partial fractions, essentially. But wind back a little bit. Let's look at what the integrals of some fractions are. Does anybody off the top of their head remember what the integral for 1 over x is?
Natural log?
Well done. Well done. Technically a plus c. There it is, right? Natural log. Now, what you won't be surprised about, but I'm just doing it for completeness, is that if you stick a 7 in the top, don't you just get 7 natural logs? It doesn't do that much. And if you have a half on top, well, let's make it even weirder, a negative a half on top, it doesn't really do anything. Would you agree that the basic part is it's some multiple of log x? So if you ever get a fraction like 7 over x, or negative a half over x, or just 1 over x, you know you're going to get a multiple of log x. And that is those guys. Now, you could get a guy, in fact, you will get a lot of guys that look something like him. I'm going to show you a shortcut. If I wanted to integrate 1 over x plus 7, couldn't I just do a u sub of x plus 7 and eventually get the right answer? But let me tell you the shortcut. Isn't it nice that the answer is very easy? The integral of 1 over x is log x. The integral of 1 over x plus 7 is the natural log of x add 7. What would 10 x plus 7s get me there?
Just a 10 on the outside.
Yeah, that's all it is. So if you have to integrate 5 over x minus 2, 7 over x plus 3, isn't this what you're going to get? You're just going to get some multiple of a natural log. Okay. How about, oh, forget that. Keep a 1. Keep it simple first. Not x add 7, but 2x add, oh, let's make it 11, so the 1 isn't that important. If you want to integrate this, you can do it by a u sub, and if you forget the shortcut, just grab a piece of scratch paper and do it as a u sub. But if you want to, this is the shortcut. Now, the 1 over 2x plus 11 gets you the natural log of 2x plus 11. But where did that darn half come from?
Is it because there's a 2 in front of the x on in the
Yes, exactly. I shouldn't have cut you off there. You were mid-flow, but yes. So what would this guy get you? Well, you'd get a natural log of 4x minus 3. Great. But what would the 4 generate?
a 1/4?
A 1/4. Isn't that basically the linear shortcut method just being used in its own right? Now that means, I guess I should do one more. Suppose you stick a 9 on there. Don't you just get 9/4 instead of 1/4? Doesn't do that much. So right now, if I gave you any fraction, any simple baby fraction, right, just on its own, that looked like any of these guys, do you feel comfortable you could do their integral without any real hassle? And that is essentially the strategy behind integrating this. You're going to take this guy and turn it into two nice baby fractions. This guy up here that's called A and B, they are going to turn into numbers. They're going to turn into 7 or 4 or -1/2, right? And when they do that, won't you be able to integrate these? So you might not be able to integrate the original fraction because it's a big ugly fraction. But if you can break it into its partial fractions, shouldn't you be able to integrate these guys? And that's how you're going to get your answer. So that's the big picture of what we're going to be doing, is taking ugly fraction, breaking it into its partial fractions and integrating these because these are easy, you know, doing things like that. Now, there is a couple more, but not too many. There's this guy. We know the integral of 1 over x squared plus 1, also written as 1 plus x squared sometimes. Where's that guy? What's his integral? It's an inverse somebody.
Inverse tan.
Yeah, that's the guy. Now, if it was 10 of these guys, wouldn't you just get 10 inverse tans? The last guy, the last thing in this list I'm going to be doing as far as integrals is this fella here. He is not x squared plus 1. He will be x squared plus 16, x squared plus 25, right? He will have a number that's not 1. This guy has an integral. And I am just going to tell you who he is. He is connected to the inverse tan, but he's not the inverse tan of x. He's x over 7. And at the front, you've got another 1/7. Can you see where the 7 is coming from? It's not just a made-up number out of nowhere. It's coming from the 49. So if you had 1 over x squared plus 25, right? 1 over x squared plus 25, you would get 1/5 inverse tan x over 5. If it was x squared plus 4, 1/2 inverse tan of x over 2. That makes sense. I'm just telling you it is, right? You could spend a whole load of math trying to prove it, but we just assume that it's true and move on from there. Any questions about what we've kind of looked at, which is how do you integrate fractions? Simple fractions, relatively speaking. Are we good with that? Can I move on? Don't hear any dissension, so I shall. So the next thing we're going to look at is how to split up a complex fraction into its partial fractions. Now, this is going to take two different stages. The first stage, we're just going to get practice at what does it look like when you break it apart. I'll show you what I mean. See how this guy here gets broken apart as some number over x plus 1 and some number over x minus 2. That's an example of that. Here are the rules for how you break a big fraction into its smaller pieces. It will get broken apart as some number over x minus 3 plus some other number over x plus 1. Do you agree that's pretty easy? Have you noticed that I don't care what the top looks like as long as it's less than x squared, it will be fine. But the two main pieces, these guys are its partial fraction. How about 2x squared plus x over x minus 1, x plus 1, x plus 2. How many partial fractions do you think this breaks into?
3.
And not surprisingly, that guy, and that guy. Now, right now, these letters are just placeholders for where eventually numbers will go, right? So that'll be 2, that'll be a half, that'll be 7, right? Or whatever it ends up being. We don't know how yet we're going to get those numbers. That's going to come, but that'll come later. Right now, you need to know what it breaks apart into as like the first step in the process. Now, we're going to show you the ugly partial fractions. If you didn't think they were ugly, imagine this one. You're going to get questions where one of the terms on the bottom will be x squared plus 4, x squared plus 1, x squared plus 25, right? It's going to have that x squared plus look to it. You are going to get an x squared plus 9, and you're going to get an x minus 3. I don't think that's a surprise, right? You would probably have guessed that. What you might not know is that this fella here, the x squared plus 9, gets an ax plus b on the top. And this guy just gets a c. So anytime you have an x squared plus a number as one of your fractions, well, you make sure that the top has two pieces to it. We'll call it ax plus b. So when that's finished, this will be 3x plus 1, 2x minus a half, right? I'll have that looked at. And these are called linear terms. Linear terms just have one number, right? One letter on the top. So would you agree it's a little bit uglier? But that's the rules for it. Now, this one throws people for a loop. It's x minus 2 squared, x plus 1. And most people think that it just breaks into two fractions, right? Something over x squared minus 2 squared and something over x plus 1. And it does break into those two parts, but it doesn't break into just those two parts. Whenever you get an x minus 2 squared and x plus 7 squared, right, a square, it breaks into two separate pieces, one without the square and one with. But all of these guys get a single letter. And that's every permutation you need to worry about. There aren't any others that we need to concern ourselves with. So if I give you this fraction, this is what its partial fractions look like. If I give you this complex fraction, this is where it's built from. These are its partial fractions. Do you feel comfortable about that piece of the process, what you break it into? Great. Good, I got a thumbs up. Can we move on now to finding the A's and the B's? Because that would be important, wouldn't it? If you want to integrate it, you need to know who they are. And that leads us to how to find the constants. Right, the A's, the B's, the C's, etc. How do you find them? Well, it's not one technique, it's two. Normally you don't do two techniques, but there's a reason why there's two techniques here. The first technique is called the cover-up method. And you can use the cover-up method when, I'll call this A, A is a bad letter, I'll call this 1, and I'll call this 2. You can use the cover-up method when both terms are linear, or where all three terms are linear. And the second method is called the general algebraic method. And you can use the general algebraic method in all situations. So that means you can use it in 1, in 2, in 3, and in 4. So what would cross my mind, and I'm sure it did the first time I learned this, was why do you need two methods? Why don't we just use the general algebraic method? It works for all of them. One method's easier to learn than two. Totally good argument. So let me try and tell you why it's worth it to have two methods. The general algebraic method works for every possible situation you could want. It has a problem. It takes forever and a day to do. It's very long. Slightly cumbersome as well, but it can be done. The cover-up method is magic. It's a shortcut. It just gets you the answer, and it gets you the answer in less than a minute. And we like shortcuts, don't we? They are quick and easy, even if they are magic. Like, I don't know why it works, but it works, right? It's magic. We like that, don't we? Because it makes our life easier if we can get an answer in a minute than in 10 minutes, right? We prefer to do the same thing. The only thing you have to remember is only use it in these two situations, right? Where everything is linear. You notice that there's no squares, right? X minus 2 squared, don't use it. X squared plus 9, don't use it. But if everybody is linear, go for it. So let's show you how to do the cover-up method. Well, let's do it for this one, right? Since it's there. I would like to find what this guy looks like when you break it into its two pieces. Now, the cover-up method is magic, and you have to look at it as just a process that works, and don't get too caught up on I wonder why it works. The next part about it is it's very visual. It's easy for me to show you it. If I wrote down what I'm about to do, in sentences in English, it wouldn't look half as obvious as it is visually. So think visual. So essentially, I am looking for this number A, and then I'm going to be looking for this number B. So here goes. Let's get A. On the bottom is X minus 3. Go over here and cover up the X minus 3. Do you see there's a little fraction left over, right? A little piece on the top left over, a little piece on the bottom, right? That's probably why it's called the cover-up method, right? So cover up the X minus 3. Now, what number should X be to make X minus 3 0?
3.
Plug that into this guy and you've got your answer. 3 lots of 3 is 9, take away 1, you got 8. 3 lots add 1 is 4, you get 8 over 4. Hey, there's your answer. It's a 2. Right? 3 lots of 3 take away 1 on the top, 3 add 1 is 4 on the bottom. 8 over 4, 2. Would you agree that's magic? There's no reason in the world why that should work. Right? Okay. Let's do the B now, right? X plus 1. I'm going to cover up X plus 1. What value of X makes X plus 1 0?
-1.
Plug in -1. Let's see what we got. -3 take away 1 was what? -4. -1 take away 3 is also -4. Hey, -1. Oh no, +1. 2 negatives plus 1. We have just done this guy. Original fraction, it splits like that. Clever. Now, suppose I was being asked to integrate this. Well, that means I'm being asked to integrate this. Well, I know the integral of this guy, isn't it 2 natural logs of x minus 3 plus 1 natural log of x add 1. I'd say, wasn't it dead easy to integrate? If you break something into its partial fractions, aren't the integrals pretty simple and therefore should be easy to do? Do you like the cover-up method? As magic as it is. Okay, let's try another one. Let's do this big ugly guy. 2x squared plus x over x minus 1, x plus 1, x plus 2. And we already know that it splits as 3 pieces. Here goes. Let's find A. Right. On the A, it's an x minus 1, so I'm covering up x minus 1. What value of x do I use? I use 1. Right, 2 lots of 1 squared plus 1, that's 3 on the top. 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 1, 2, 1, 3, 6. So I end up with a half. And I know that looks ugly, but leave it like that because that's actually helpful. Okay, let's do the x plus 1 guy, right? The B. Cover up x plus 1. Would you agree that the value of x I'm going to now use is -1? Okay. 2 lots of -1 squared is 2. Take away 1 gets you 1 on the top. -1 take away -1 is -2. -1 add 2 is 1. -2 times 1 is -2. Oh, I get -1/2 on the sine one. Let's go for C then. Cover it up. The value of x I'm going to use is -2. Okay, 2 lots of -2 squared is 2 lots of 4, that's 8. 8 take away 2, 6 on the top. -2 take away 1 is -3. -2 add 1 is -1. -3 times -1 is +3. And it looks like I get 2. Are we happy with the partial fractions that we got out of this fella? We good? Right. Let's stick an integral around it and call it dx. This fella gets you a half natural log. See, it's just better to leave it like that. This guy gets you -1/2, that log. And doesn't this guy get you 2 times that log? Add C, and you're finished. The integration was probably the easiest bit of the whole question, wasn't it? Okay, I'm going to give you 2 to try, because that's the best way for us to make sure that we're cool on that. I would have given you one of those earlier questions, but wouldn't that be 20 minutes out of your life that we don't have time for? You know, if we did the earlier stuff. So here goes. Okay. 1 minute, 1 minute. You got 2 minutes to do both those guys. I will give you the start, because that's the easy bit. Find A, B, and C, and if you've got time, integrate the damn thing as well. Just find A, B, and C. If you can do that, that's your goal. If you have extra time left, integrate the damn thing as well. And no pressure. You've got 1 minute, 50 seconds now. Oh, you finished, Ben. Well done. Okay, that's us. Okay, a lot of stuff going on here. Let's see if we can cut some corners. I want to get the number here, right? So x minus 2, cover this up, plug in 2. That's 9 on the top, negative 2 on the bottom, so what, negative 9 halves? Can't really see many of you. You've all disappeared as pictures. Agreed? Okay,
Yes.
we're good. Right, on to B then. You're going to use 4 this time, aren't you? So cover this up. 16 add 1 is 17, 17 over 2. So what would that be? Negative 9 halves, the natural log of x minus 2, plus 17 halves, the natural log of x minus 4 plus c. Let's look at this guy. What value of x, because I never did this, what value of x do you use?
I use 0.
And that's exactly what you should have used. It's kind of a silly question, but sometimes silly questions catch you out. What value of x makes x 0? Oh, x equals 0 does. Yeah, it's kind of silly, but it is true. Right, so the top's negative 1, and the bottom looks like it's negative 3, so I make it plus 1/3. Got 2 nodes on that. Okay, the middle one, x minus 1. Okay, so in this case, we're going to plug in 1. So cover up the middle term. 2 lots of 1 take away, that's 1 on the top, and 1 times 4, I make that a quarter. Does that look good? Got 1 node on that. Well, that's not good, because I could be wrong then. X equals 1. 2 lots of 1 squares 2. Take away 1 is 1. 1 times 4, no, I'm good. Right, last one. Negative 3 gets plugged in here. Ooh, it's going to be messy. 2 lots of 3, that's 17 on the top. And 3 times 2 is 6 on the bottom. I get 17 6. Does that look good? No, it's not good. I didn't do it right. I'm sure I didn't do it right. Let's check again. Plug in negative 3. I'm happy about the top. Negative 3 times negative 4 is negative 12. Right, I get 17 twelfths. Does that look better? Two lots of negative 3 squared, take away 1. Negative 3 times negative 4. 9 times 2 is 18, take away 1. Positive 12. Positive 17 twelfths. Okay, 3rd time lucky. Positive 17 twelfths. Does that look good? At last, I got the nodes I was looking for. Okay, now you want to integrate that. You're going to get 1/3 natural log of x. Add a quarter natural log x minus 1. Plus, because it ended up being positive 17 twelfths, that fella, plus c. So you should be able to integrate any fraction that has linear terms on the bottom. That's essentially